Hi, Brendan here from Energy Training Group with another training video on helping you calculate your system yield for a PV system. So let's get started. How do we calculate system yield? So system yield, how much energy our PV system is going to create, is calculated as irradiance, which can be represented as peak sun hours or kilowatt hours per meter squared per day, multiplied by our system size, multiplied by system efficiency. So let's look at an example problem and then we'll go through how we calculate that. So our example problem, we have a system size of 4.5 kilowatts. It's a flush mounted system. We get 4.2 peak sun hours after allowing for tilt and orientation. So that's our radiance that's going to fall on our PV modules. We've got a shade loss of 6%. We have an average ambient temp of 22 degrees Celsius. Our inverter efficiency is 96%, and our volt drop on our AC and DC cables is 1.5%. And finally, our PV module temp coefficient of Pmax is minus 0.32%. So to calculate efficiency, we have to calculate the total efficiency of the system. Okay, the other two figures in our formula are pretty easy. Obviously, irradiance, we get given that as a figure. Our system size, we know what our system size is. There's a bit of work to work out what our total system efficiency is. So that's what we need to calculate. So the first thing we want to do that's nice and easy is to convert all of our ones that are presented as losses, and we convert them to efficiencies so we can put them into our formula. So to calculate an efficiency, you just subtract your loss from 100%. So our shade loss was 6%. That means it's 94% efficient. Our volt drop was 1.5%, therefore it's 98.5% efficient, right? So you're just subtracting the loss from 100% to convert it to an efficiency. Now the big one is to calculate temperature loss. Okay, so we must include temperature loss in our efficiency calc, and this is the part that takes some time to calculate. Now we need to calculate temperature losses, and this is also known as fTemp. Alright, so we must include temperature loss in our efficiency calculation, and this part takes some time to calculate. It's not quite as easy as just doing a conversion from a loss to an efficiency. So the first thing we need to work out is we need to calculate what our average cell temp is. Okay, so we assume that our cell temp, right, is 35 degrees above ambient for a flush mount array, 30 degrees above ambient for a tilt array under 20 degrees tilt, and 25 degrees above ambient for arrays over 20 degrees tilt, ground mounts or pole mount arrays. Okay, so these figures, we take them from the CEC design guidelines. Okay, so that's where those assumptions about cell temp being above ambient temp come from. Now we also need to remember that PV module specs are measured at STC, okay, standard test conditions. And standard test conditions are measured at 25 degrees Celsius. So let's calculate our average cell temp above STC, or standard test conditions. We take our average ambient temp, we add our expected cell temp rise, and then we minus standard test conditions. Okay, so in this particular problem, we assumed we had an average ambient temperature of 22 degrees. Our array was flush mounted, so we add 35 degrees, and then we minus 25. Okay, so that's our standard test conditions temperature, and we can see that we're going to assume that our panel is on average 32 degrees hotter than standard test conditions. So that's what we'll use to calculate our temp loss. Now to calculate our temp losses, we need to use the temp coefficient of Pmax from the module that we're using. Now we haven't chosen a particular module for this problem, right? We've just been given a temp coefficient, and that is minus 0.32%. So first we convert that to a decimal. Okay, so as a decimal that looks like 0.0032. and then we will multiply our temp coefficient by our average cell temp above standard test conditions. So our panel is 32 degrees above standard test conditions. Our temp coefficient is 0.0032. So we multiply 32 by 0.0032 and we get 0.1024 or 10.24% loss. Now to convert that to an efficiency, we subtract from 1. So 1 minus 0.1024 equals 0.8976 or 89.76% efficient. Now we're going to calculate our total system efficiency. So our calculated efficiencies are 94% for shade, 96% for inverter efficiency, volt drop was 98.5%, and we've now calculated our temperature efficiency at 89.76%. So to combine these into a total efficiency, first we convert them all to a decimal, and then you multiply efficiencies together to combine them. Okay, you don't add them or anything like that, you multiply them together. So if we do 0.94 times 0.96 times 0.985 times 0.8976, we get a total systems efficiency of 0.7978 or 79.78% total system efficiency. Now we've got all of our figures, we can calculate our system yield. So remembering from the first slide, system yield is calculated as radiance times system size times system efficiency. We had 4.2 peak sun hours, we had a 4.5 kilowatt system, and we have calculated our system efficiency at 79.78%. So we can see 4.2 times 4.5 times 0.7978 equals 15.07842 kilowatt hours per day, right? That is our expected average system yield. It's important to remember this is obviously an average figure, okay? So if you were going to do a proper system yield, you would usually calculate, do this calculation for each month of the year, given that the available irradiance is going to be different for each month and that the expected average temperature is going to be different for each month as well. And then you would work out your figures across an entire year rather than just for 1 month. Now the other way you might need to do a system yield calc is to calculate system size, right? So instead of being given a system size and being told to calculate what is its expected yield, you'll be given a target output, and then you'll have to calculate what size system you need to design to meet that requirement. So essentially you follow the exact same process for one module, right? And then you can divide the output of one module into your target yield, and that would work out your required system size. So a really quick example, right? We've got a target of 22 kilowatt hours per day. We calculate that one 350 watt panel will produce 1.3 kilowatt hours per day using the process we've just gone through. We divide 22 kilowatt hours by 1.3 kilowatt hours, and we see that we would need 16.92 350 watt modules to meet our required output of 22 kilowatt hours. And then we'd obviously round that up, okay, because you wouldn't want to, if you went to 16 modules, you would come up short, so you round up to 17 modules. That is it. That's a quick video just explaining how to calculate system yield. I've had quite a few guys struggle with that, particularly the fTemp section, so hopefully this is helpful. As always, if you need any help, make sure you're reaching out to me via WhatsApp or via email, and good luck.